final in CRF. Transformation potential, or you can write simply GO potential plus solid tide. It was direct third body plus solid tide plus ocean tide, so R acceleration plus relativity or GR general relativity plus R dot solar radiation plus air drag plus thermal effect. All these things are perturbations. Of course, some people, they consider that, I should explain it, but I do not do that. They consider the central field, the spherical Earth, as the main, and also they consider the effect of or the contribution of higher order terms of the gravity, which comes from the spherical harmonic. They do not consider the 0 degree. It's from the rest. They will consider this one as geopotential perturbation. So it's for the case that you do not consider the 0 degree of the first of VR, the derivative. So if they call this geopotential, so don't be surprised if they say that geopotential perturbation. It means that the acceleration vector due to the gravity x without the 0 degree term, because 0 degree term can express the Earth's sphericity. So, and the higher degree harmonics comes from the non-homogeneities inside the Earth. So don't be surprised. So if they call it this is perturbation, these are the perturbations for the satellite orbit. And when you can determine these things, you can simply take them to the other side and correct the true satellites through acceleration of the satellite. What remains here will be only the part which is related to the gravity field. So if I correct this one, I have the satellite acceleration considering all perturbations. How can I determine the gravity field? That's really simple then. Let me clean. Then I have true satellite total minus, what was that, direct effect minus solid tide minus ocean tide minus general relativity minus R dot solar radiation minus air drag minus thermal effect is equal to gradient of the potential, which is, these are three-dimensional accelerations, and we have this derivative of v with respect to r, derivative of v with respect to r theta, derivative of v with respect to r sine theta. Yeah, that's all. So one way to do so, to solve this system, the first one, Yeah, we write VR instead. Summation, and from 0 up to infinity, r over r, m plus 1, summation m minus n, v and m, y and m theta. So I have an observation equation, and the unknown parameters are the spherical harmonics. I can write a system of equations for each point that the satellite is there. And then I can determine the value, the spherical harmonic coefficients. That's all. For v theta is the same, 1 over r, or m plus r. Oh, I wrote wrong here, m plus 1 over r, and m plus r. The same thing here, v and m, this time derivative, and v lambda exactly same, not same, similar, v and m, this time derivative sine theta and the lambda. So for each point of that the satellite has outside, we have the true acceleration. This true acceleration is corrected for the perturbations. What remains is the contribution of the gravity field, the gravitational potential. And for each point, 3 equations can be written connecting the accelerations to the spherical harmonic coefficients. And how many equations can we have? No, let the satellite works months or years around this. You will have millions of points and millions of observation equations. And when you limit the maximum degree of spherical harmonics to some degrees of 20, you will have limited number of spherical harmonics coefficients to estimate. So you will have always larger value of observations. And one important factor is that you need to have global coverage of the data, which you will have this in satellite geodesy. So you need to wait until the satellite can cover the whole Earth, at least cover the whole Earth to compute the spherical harmonic. The denser data you will have, the more spherical harmonics you can estimate. Yes. Or you can apply spherical this boundary value problem of the vector gravimetry that we have already discussed. But the problem is that the data are not at the surface of the sphere, that you can simply take the integration and use this vector gravimetric boundary value problem. You can use least squares in that case simply. Or you can change it to what's called to the integral formula to gravity anomaly at the surface of the Earth, or the potential at the sphere, and with the Poisson integral invert the data locally over the area. That will work fine for this. But if you want to determine the spherical harmonics all over the Earth and use this solution of gradiometric boundary value problem, not the gravity inversion, not the integral equations, then you need to interpolate all data on the mean orbital sphere. That could be one.